I probably put in last night, right? Like, pretty sure it's like 40 something or something. We have put it in for a little bit. Oh, that's 70% of Just close it on. I'll put it in my phone.
Hello, Dr. Chan. I was wondering if you can help explain all the numbers. I'm having trouble like kind of finding essentially what I need to find.
Sure. Essentially. Back never seems to.
This one, right?
Yeah.
Okay.
The last one.
Yeah. So for this one, you know, I'm showing you two muscle forces here, but
Yeah.
only one of them are going to be active. So
Like if you solve for both of them, will one turn out like 0?
Well, you can't solve for both because you only have 3 equations, right?
Okay.
And you only have and you have 3 unknowns. So it's either going to be one muscle force and 2 joint reaction forces, or the other muscle force and 2 joint reaction forces. And so you kind of have to use some intuition before the problem starts to kind of see which muscle force is going to be active.
Yeah. Okay.
And so for the good posture one, and so that's kind of when you're standing up, kind of really straight. And so you can kind of imagine, you can kind of tilt your back. You can kind of feel your abs kind of acting. And so in that case, we assume that FMA is going to be the one that's acting, and then we just ignore FMB.
Okay.
And then we solve for FMA and the 2 joint reaction, which is kind of what we see here.
So like for there, you're leaning forward, so it would have to be your back.
Yes.
Okay.
So,
I wasn't sure about that because it says determine which force, but I wasn't sure if you meant like intuition wise or solve for both of them and one should come out 0.
Yeah.
Or something like that.
It's intuition wise.
Okay.
Yeah.
Okay, so then from intuition, you solve for the magnitude of the force that actually applies to it, and then the reaction forces.
Exactly.
Okay.
And then eventually, you're going to get to part 3, where from part A and part B, you'll see that there's kind of a balancing act between the 2, and so it all really depends on this angle right here. And so there's a certain angle or certain posture that you can have where neither of them are active. So it's like you have kind of a perfect balance of like the weight, all the weights involved in this problem actually.
Okay, so we're gonna find the theta where the muscle forces and everything else is just cancels out because there's nothing.
Right. So both the muscle forces are 0. So you're going to assume both FMB and FMA are going to be 0. The weights are still going to be active, and you just need to figure out what that angle is. So you would use the same equations, but assume the muscle forces are 0, and then the unknown in this case turns into the angle, not the muscle forces.
Okay, I think I get that one more now. For the second one, when I was having trouble with the hip joint, I know in the notes you gave them direct measurements, like just LM, HM. But so like in the test, if we have something like that, we can't just assume the hip joint aligns with this.
Exactly. Yes.
Okay.
Yeah.
So just
Yeah. So kind of always do it based off the measurement. So the figures are sometimes not going to be to scale.
Yeah.
And so you have to do it just based on the measurements that are given to you.
Okay. That took me forever. I was like, dude.
A few people have questions.
Yeah. Okay. That makes more sense. Thank you.
Yep.
That's like. Yes. Over there. Yeah. Oh, okay. I don't get emails from my. I only get emails. So bigger. I think this is a shot. Instead of going, and I get the table. Instead of so now you're sharing. It's sort of honest. He was just like FYI. Like that's. Bro, I'm just gonna like shots my. Thank you so much. Asking. He's 6 months now. Great. Looks so slow.
That's it.
Yep.
Off the top of your head, do you remember what the date was to be able to apply for priority registration? You were gonna apply to graduate next year?
As long as it's before the registration date, I think it's fine. Oh, what date the actual priority registration is?
Or no, not the actual date, just if you pay for it beforehand, you get the chance for priority registration.
My understanding is that as long as it happened before the registration window, it's fine.
So I think the registration window for spring would be somewhere in spring, right?
No, so for the spring semester courses would be end of October, early November.
Oh, okay. But that's, I mean,
G.
Alright, it's 4 o'clock, let's go and get started. Alright, good afternoon, everyone. How's everyone doing today? Good? Are feeling good? The midterm this week? Okay. Alright, so we have a shortened week in terms of lectures this week, so we have just one today. And then of course, Wednesday's our midterm exam. So I'll send an announcement just to kind of remind everyone and just to kind of clarify what material we're bring. But I just finished writing the exam actually just maybe about an hour ago before the time. So yeah, so it's pretty similar to the homeworks. There's only 2 problems actually. Because I kind of timed myself, and with 3 problems it took a little bit too long. And so it's only two static analysis problems. But then I did put more conceptual questions. So there's 6 short answer problems and 2 static analysis problems. So, but it's not a long exam at all. So I think time shouldn't be an issue with the exam. But I'll kind of summarize this all. Yeah.
so we'd still be good if we just studied the homework and not like the actual problems and stuff.
Well, I mean, study everything that I gave you, of course. I mean, the more the better. But it's if you could do the homework problems and you really understand them and you can kind of do them without looking at the solutions, you're definitely in a really good shape. But with these kinds of problems, the more practice you do, the better it can be. And definitely study the study guide as well. The study guide is going to be your main resource for the conceptual. Which are a bigger proportion than before. So right now, the proportion of the points is going to be 60%. It's going to be on conceptual questions. That mostly is going to be a lot of bone biomechanics, muscle biomechanics, which didn't really have any problems. And so I'm asking a lot of questions on that, and then 40% will be on the static analysis. I'll summarize this just so everyone. And just a reminder, you can also bring a sheet of notes, so 8.5 by 11 sheet. Both sides, you can write it, you can type it, whatever you want. And then just bring a calculator and you're writing your pencil. Okay. So the plan for today is I actually have one more set of lecture notes on static biomechanics, which is based on the spine. Okay. And so we're going to talk about the spine. I have a couple example problems with the spine today. But I think what you'll see is that, at this point, I think everyone's kind of getting used to doing these static analysis problems. And so I think what's kind of more interesting about this section here is just a lot of the kind of the concepts with the spine and kind of how it's a little bit different from the upper and lower extremity. Because there's some kind of unique issues that kind of come with the spine that we don't really see in the other parts of the body. All right. I think that's about it for my announcements. Are there any questions I can answer before we get started for today? Oh yeah, I'll post a solution for homework 3 tonight as well. So basically, right after it's due, I'll post a solutions on Canvas, just so you'll have that as a resource for students. Okay. All right. So let's go ahead and get started then. Okay. So let's talk about the spine, right? And so the spine, most people, when you think of the spine, you think of the main kind of spinal cord that kind of runs on the back of your body, and that's basically what we're going to be focusing on today. Okay, and so when you compare it to the upper extremity and the lower extremity, the spine has the least amount of flexibility, and so there, of course, you can move your spine, you can move your back, but when you compare it to the range of motion that's available in your upper extremity, your arms and your fingers. Even with your lower extremity, with your legs and your feet, the spine has the least amount of mobility. Okay, and the main purpose of this is that it's mostly just like a structure. It's mostly a connecting structure. And so, on the one hand, your spine bears a lot of the weight of your body. So, in that sense, it's very similar to the lower extremity, but it also has a lot of other capabilities as well. And so on the one hand, it's the main thing that connects the upper part of your body to the lower part of your body, at least in terms of the bones, right? And so, if you look at, all the bones in your upper extremity, your chest, your arms and stuff like that, and all your lower extremity, the only bone that really connects them is your vertebrae. There's a lot of soft tissue and muscle that connects them, sure, but the main thing that connects the two to provide kind of one uniform structure for your body is the spine, right? So for that reason, the spine is kind of important for that. And I think probably the main function of the spine that people kind of mostly associated with it is that it protects the spinal cord. And so the spinal cord is this kind of big bundle of nerves that goes from your brain to the rest of your body, and it's kind of the central part of your nervous system, right? And so because it's so important, you need kind of a strong kind of robust structure to protect this. Because if you get damage to the spinal cord, it can cause a lot of other issues in your body, like paralysis. Okay. And so when we're talking about muscles of the spine, we're mostly talking about the core muscles, and so your abdominal muscles, your lower back muscles, and your lateral muscles as well. Okay. And so they provide for a lot of motion, but not as much as the upper and lower extremity. Okay. And so in terms of classification, we classify the spine into 5 different sections. So the first 3 are kind of the main ones. So, we're going from the top and bottom here. So we have the cervical spine, which is the part that mostly connects to your skull. We have the thoracic spine, which is your upper back. So that's what all these vertebrae are. And then we have the lumbar spine. So that's the lower spine right here. Okay. And then the last 2 parts of the spine, the sacrum and the coccyx, are part of your pelvic bone down here. And so those are basically the 2 bones that consist of your tailbone. That's what we call it. Okay. But for the most part, for our analysis, we're actually we actually mostly focus on just kind of one part of the spine here, which is the lumbar spine, which is where most issues, when people say they have back issues, most of the time it's due to the lumbar spine. So we're going to be focusing mostly on that, just because that's the most interesting from biomechanics. Okay. Okay. So this figure on the right here kind of shows you kind of the classification of all the different parts of the spine. Okay. And so your spinal column actually consists of 33 vertebrae bones, which are all kind of stacked on top of each other. Okay. And so the number of vertebrae bones in each section is kind of broken down according to this breakdown here. So most people have 7 cervical spine, and so they're labeled C1 to C7, starting from the top. Okay, so it's the C1 and C2 bones. Those are the ones that kind of insert into your skull, and then as you go lower, they're labeled C3, C4, C5, C6, C7 at the bottom. The thoracic vertebrae is your upper back. So this one has the most vertebrae bones. So there's 12 here. And they have a very similar naming convention. So they're labeled T1 on the top, all the way down to T12 at the bottom. Okay. Your lumbar vertebrae are these kind of the big ones at the bottom here, and so there are 5 of them, and so those are labeled L1 to L5. Okay, and then you have 5 sacral bones, which are kind of all fused together, and so it's a little bit hard to see from this figure here, but you can see there's from here you can kind of tell that they have kind of a similar structure as the vertebrate bones, but they're all kind of fused together. They don't really have kind of a space in between them like the other part of the vertebrae. Okay, and then you have kind of the small tailbone at the bottom right here, which is your coccyx bone. Okay, and so I say on average because there is some kind of person-to-person variation in terms of the number of vertebrates that people have. And particularly, there's the most variation in lumbar vertebrae. And kind of an easy way to tell when you kind of switch from one section to the other is to look at the curvature of the spine. So if you look at the cervical spine, the cervical spine kind of curves this way, and the thoracic spine kind of curves this way. Okay. And so this curvature, so this right here is your back. If you're kind of looking from this perspective here, this is kind of the front of your body. The lumbar spine kind of curves, the inner part of the curve is towards your back as well. And then, even down here, the curvature kind of changes as well. So that for the sacrum, it kind of curves this way. And then the coccyx kind of starts to curve a little bit that way as well. Or it kind of starts to, but then for all intents and purposes, we always kind of want one part just like that. Okay. And so when you're looking at the vertebrate bones, the curvature of the spine is important because that's how you tell when you go from kind of one section to all right. Any questions on this so far? Okay. All right. And so, before I kind of move to the next slide, another thing that I want you to notice as well is that, if you compare the size of the bones up at the top, and you compare them to the size of the bones at the bottom, you can see that the vertebrate bones kind of grow in size as you get closer to the bottom. And there's a very kind of important mechanical reason for that, because as you get lower and lower on the spine, you start to have more and more weight that's being applied onto those bones. Okay? Because if you compare the vertebrate bones at the top, the really only weight that's being applied on the cervical spine is just from your head, from your skull, right? But then when you get towards the bottom, the lumbar vertebrae is bearing the weight of everything above it, as well as the different parts of the body that are associated with it as well. Right? And so it's very similar to how you would kind of construct a just an engineering structure, right? And so you almost always want to construct things with a strong base, with a wide base, and then you can kind of taper it off as you go up above. So the vertebrate bones kind of follow that same function. Okay, and so let's talk about these vertebrate bones. So they're kind of very unique in structure in terms of how they serve their purpose. Okay? So each individual vertebrate bone is kind of given by this shape right here. Okay? And if you want to look at kind of a top-down view of it, it's shown right here. And so the different parts of the vertebrate bone is we have the body. So the body is kind of the main kind of load-bearing part of the vertebrate bone, which is kind of this part right here. Okay? We have a hollow ring. Okay, so there's a kind of a hollow ring inside the vertebrate bone, which is where the spinal cord goes through. Right? And then we have kind of these parts that kind of stick out. So they all have kind of different names, for each different appendage. But for our purposes, I just call them the bony appendages. So they're the things that kind of stick out from the vertebrae. Okay? So most of the vertebrae have this same structure. The only exception to this would be the top 2 cervical vertebrae, so C1 and C2. And so their appendages are kind of shaped a little more specially just so that they can articulate with the skull. Right? So just to make sure your skull can sit on top of your spine, C1 and C2 have a little bit of a specialized structure. But for the most part, all the other vertebrate bones have the same structure. Okay. Okay. And so just like I mentioned, the vertebrate bones, they do vary in size. And so, no 2 vertebrate bones are exactly the same size. And the reason for that is your lower vertebrae, particularly your lumbar spine, has to carry the weight of everything that's above. Okay. All right. And so for these kind of appendages on the outside, they do a little bit of load bearing, but there's not that much contact between the appendages of different vertebrae. But their main purpose is to kind of limit your range of motion, right? And so if you notice, you can bend forward really, really easily. But if you try to bend backwards, there's something that always stops you. Even for the most flexible people, right? And so you can never kind of contort your back too much. And the reason for that is because you have these kind of appendages on the back that kind of hit each other and prevent that motion. The reason for that is for safety reasons, so that your abdominal muscles generally are weaker than your back muscles, and so if you kind of bend too far backwards, it's a little bit more difficult for you to kind of get back to normal position. So most people they have these appendages in a good position to kind of prevent too much backward motion. Okay. Any questions on that? Okay. So let's talk about in between the vertebrae. So in between each vertebrae, and that's not counting the sacrum at the bottom, you kind of have almost like a cushion in between each one. And so we call these the discs, in particular the intervertebral discs. Right? And so these discs here, they're made of very kind of fibrous, kind of almost like a cartilage type of material, and their main purpose is to basically act as like a cushion. Right? And so just like we talked about in other parts of the body, whenever you have a joint in between two bones, there's always some kind of soft tissue there to kind of prevent the bones from hitting each other. And your vertebrae is no different. And in fact, it's probably most important for your vertebrae because of the way that we stand up and the way that the spine kind of bears our weight, and the fact that there's so many vertebrae bones. We need to have a good kind of cushioning system to make sure that our spine doesn't get damaged. Okay. And so mechanically, you can almost think of them like a spring. So this figure down here kind of highlights that really well. Is that and so mechanically, people have found it's almost like you have like a rubber ball in between your two vertebrae and a spring that's kind of on top, right? And that's what it kind of feels like. Where if you kind of take two vertebrae bones and kind of squeeze them together, kind of the sensation that you kind of feel is that there's a spring and a rubber ball between. Okay. All right. And so normally, these discs are there, to prevent injury, but they themselves can get injured as well, right? And so you may have heard of a type of injury called a hernia. And so a herniated disc. And so a herniated disc basically happens when you press your vertebrae so much that the discs actually start to bulge out. So they kind of lose their properties of kind of springiness. And you have, usually it kind of bulges out this way. This is kind of the way that it bulges out. And if it bulges out so much that it starts to pinch on your spinal cord, that's when people kind of feel that really intense kind of burning pain that's associated with back pain, because you have kind of something that's pinching or kind of pushing on literally the biggest nerve that you have in your body. So when you have that herniated disc, it's extremely painful, and maybe I know my uncle has had herniated disc before, and he literally could not move to get up because of the pain that he's in. Right? And so you can have a disc bulging. You can also have a disc kind of slipping out of its socket. So that one's a little bit more extreme and not as common, but it's kind of the same effect. If the disc is kind of pinched so much that it starts to kind of squeeze upwards, and it starts to pinch on that spinal cord, it can cause you a lot of pain. Okay. And so what can cause this hernia, these discs to bulge out or to slip out, is if you expose your spine to an extreme amount of forces. Which we'll talk about later today is actually kind of easier to do than you can imagine, right? And so, particular for today, we're going to do a couple of examples based around proper lifting techniques. So, when you're lifting a heavy object off the ground, people always tell you that there's a proper technique to doing so. Because if you don't do it correctly, you can really injure the back. And herniated discs are kind of one of the most common ways that can. Okay. All right. Any questions on discs? Okay. Okay, so let's talk about curvature a little bit. Okay? So the curvature of the spine is an important characteristic, of the spinal column itself, and that curvature is kind of designed to kind of make sure that your body is kind of well equipped to bear its own weight, in kind of the most efficient way possible. Okay, but with that said, there is some kind of what we call it, pathological curvatures of the spine. And so Probably you're familiar with the term scoliosis, and so scoliosis is something that's being checked for a lot of kids nowadays. And so scoliosis is kind of an irregular kind of curvature of the spine. In particular, scoliosis is kind of when it curves to the side, which it shouldn't do that. But you can also have irregular curvature kind of in the other directions as well. Right? And so in particular, we have a couple of the more common ones here. So we have lordosis. Okay? So lordosis is kind of an exaggeration of the lumbar curvature. And so for a normal person, you have some curvature in your lumbar spine, and that's perfectly healthy with for a good posture. But for some people, they have kind of an enhanced curvature of their lumbar spine. Okay? And you can enhance this kind of artificially as well. So you can use your back muscles to kind of stick your butt out, and what we say is that you're kind of putting yourself in a lordosis position. But some people just have this pathology as well. So they're just standing straight, not really doing anything. And if you have kind of an enhanced lumbar curvature, we call that lordosis. Okay. All right. So the one that's kind of probably more prominent that I think kind of stands out to people more is enhanced thoracic curvature. Okay. And so you have kind of an enhanced curvature of your thoracic spine. Right. So visually, this looks like kind of someone having a hunchback. And so kind of the medical term for this is kyphosis, right? And so this is most of the time for most people is an effect of you're either born with it, and so a congenital abnormality is something that you're kind of born with, or it can also occur due to osteoporosis. So for older people who start to have their bones kind of start generating, okay, sometimes they naturally kind of form this this shape. And of course, the one that probably most people know about is scoliosis, and that's when you have kind of a side-to-side curvature of the spine, kind of this way. When if you're looking at someone from the back, your spine should kind of make a nice kind of straight line. Okay? And so I think that's part of the reason they kind of check it for kids, because it's relatively easy to spot. And if you kind of spot it early, then there's a lot of physical therapy and things that you can do to kind of correct that while your body is still developing. You don't want kids to have that abnormal curvature of the spine so early, because it can develop into a lot of other health issues. Okay, so those are kind of the descriptions of the different curvatures of the spine. Okay. Okay, so let's talk about the muscles. And so there are, like I mentioned, when we associate with the spine, we're mostly considering our core muscles. So that's our abdominal muscles and our back muscles. Okay. And so we have the abdominal muscles in the front. And so, if you have a ripped abdominals, it starts to show. So you can have like a 6-pack. But technically there are eight muscles here, and so you can have up to an 8-pack, which is very impressive. Okay. And then you have your oblique muscles, and so those are on your sides. So I don't have them pictured here, but those are the muscles that are kind of on your sides, kind of, so they allow you to kind of bend to the left and the right. Okay. But the muscles that we're going to focus on, for the vast majority of this are your spinal erector muscles, which are your lower back muscles. Okay. So those are muscles kind of right above your butt. Okay. So those are these muscles right here. And so these are the main muscles that are associated with keeping your balance. So making sure that you're standing up straight. When you're carrying a backpack or when you're carrying a load in front of you, usually it's your spinal erectors that are acting. Okay. And basically the actions of the spinal erectors, basically we can associate this with a lot of issues that people have with their backs. Okay. And kind of the upshot, or kind of the goal in short of having good posture, having good technique, is to try to alleviate as much load as you can from these spinal erectors as possible. Okay. Because these spinal erectors, they're very, very strong muscles. Actually, they're some of the strongest muscles that you have in your body. But if they're kind of acting too much, if they're exerting too much force, it's actually not really the erector muscles that kind of get injured, but it's kind of the effect that it has on all the other parts of your body. So we're going to do some examples in a second, where we'll see that if your spinal erector muscles are kind of exerting too much force, what that's going to do is that it actually pinches, or it actually kind of squeezes your vertebrae together so much. And these are the things that causes hernias and back injuries and things like that. Okay. And so, relieving the spinal erector muscles is something that, something that you kind of always want to do, just for good kind of biomechanics and good, maintenance of your body. Okay. Okay. All right, and so with that, any questions on this before we jump to the calculations examples? Okay, all right, so let me go ahead and jump to the iPad here. Okay, so let's talk about, let's do a couple of examples with spinal biomechanics. And so, you know, mathematically, these are going to be exactly the same as what we've done for the upper and lower extremity, except, you know, we're going to be doing more examples that are kind of more consistent with that. Okay. Okay. So let's focus today on lifting technique. Okay. Let's do an example. Lifting. So let's do some calculations to see, you know, what the effect of different lifting techniques are and how that affects your spine. Okay. All right. And so if you've ever, had any kind of work where you're lifting kind of heavy objects on a regular basis, you know, there's always some kind of training in terms of what's the proper technique for them, right? And kind of the way that it's most commonly described to people is that when you're lifting something from the ground, you should always lift with your legs, don't lift with your back. And so let's say that, you know, you have an object on the ground, and so we're just gonna draw it as a box. Okay. So the bad way or the poor technique way to pick up an object from the ground is to, you know, kind of bend your back. And so to keep your legs straight and kind of bend with your back to go down, right? And so the poor way to do this would be like this. So you keep your legs straight, you're kind of reaching down like this. So this is bad idea. And the reason for this is that, you know, when you're doing this, you're putting all the stress on your spinal erector muscles right here. Okay. Your leg muscles are doing a little bit of work just supporting your weight, but the main muscle that's actually going to lift the load off the ground is going to be that spinal erector muscles. And in fact, you know, it's actually doubly bad too, because when you're kind of bending over like this with your legs straight, you know, it puts your muscles in kind of a not so great position in terms of, you know, the angle and the attachment distance as well. Okay. And so the good way to lift would be to actually to bend your knees, okay, keep your back straight. Okay. And then and lift like that. And so the main kind of characteristic here is that, you know, the back is kind of straight up, right? So you're not kind of bending forward anymore. And so you're not putting that kind of extra stress on your spinal erectors. And, you know, you're offloading a lot of that load to your legs, okay? Okay. All right, so let's do a static biomechanical analysis of both situations, and so we can see, you know, we can actually compute how much stress that's putting on the back. Okay, so let's do the poor technique first. Okay, so the poor technique looks something like this, and so let's say that, you know, we have someone, He's standing up straight. Okay. So there's minimal bend in his legs. You can see that his his legs are straight. He's bending over. Okay. And so the main joint that we're going to look at is this one right here. So this is your hip joint basically, or your back joint. And so just like we usually have, we're going to have our joint reaction forces. And so we have JY, JX. Let's draw our muscle force. And so our muscle force is going to be like this. So we're going to assume, we're just going to keep things simple today. So, we're going to limit the amount of geometry that we do. And so let's assume that we know the exact moment arm for the muscle force. And so we'll call that distance A. Okay. We also have the weight of the leg. And so we have the weight of the leg that's kind of supporting this in the level. So the weight of the leg, we're going to assume acts at the knee. And so the weight of the leg is going to be offset the front of the back joint a little bit. And we'll call this distance B. Okay. And so B is exactly the moment arm that we need for the weight of the leg. Okay. And then to model the amount of weight that we're carrying, we're going to model it as a normal force that's acting right at the tip of the toes. Okay. And we're going to have two contributions here. So we have the weight of the top of the body. So that's the weight of your torso. Plus WL, where WL is the WL is the weight of the load itself. And then we're going to assume a distance of C, in that direction. Okay, so let's put some numbers on this just so we can plug it in. So let me go ahead and define the three distances first. And we'll do this in kind of a somewhat of a general way. So we'll assume all the distances are defined relative to the height of the person's body. Okay, so little h here is the height of the person's body. But what you will see is that in our equations, that h is going to cancel out. Okay, and what you'll see is that we'll get kind of a good percentage answer. So it doesn't really matter how tall you are. This example will kind of show you just how much load is being put on. Okay. So let's go ahead and define the weights. And so let's say we have the weight of the leg. And so I'm going to do the same thing here. And so I'm going to define everything in terms of, relative to the weight. In this case, I'm going to define everything relative to the weight of your torso. Okay. So we're going to say the weight of the legs is about 40% of the weight of the torso. And of course, the weight of the torso is going to be the weight of the torso, right? So we're basically defining everything relative to the fact. And then the load that we're carrying is going to be about 30% of the weight of the torso. Okay. So not an unreasonable amount of weight, but a pretty decent. Right, so for, and maybe for, for an average person, their torso probably weighs somewhere in the ballpark of maybe about 100 pounds. And so, we're talking about maybe a 30-pound weight. So, definitely not unreasonable. You can imagine, maybe like a bag of cat litter or something like that. But, pretty decent amount where you have to kind of think about how you're. Okay. Okay. Oh, one more thing. We need the orientation of the muscle force. And so we're going to say that the muscle force acts at an angle of theta with respect to the vertical. So we're going to assume theta is equal to 45 degrees. So we're keeping things fairly simple today. All right, so our objective in this problem is the same as our usual problem. So we want to compute the magnitude of the muscle force. As well as the joint reaction forces. Any questions on just the geometry of this example, or kind of what we're looking for? Okay. All right, and so we're gonna go about this in roughly the same way. Okay. So let's go ahead and write our moment balance and our force balance. And so just to kind of make things a little bit quicker, let's start with the moment balance. And so from the moment balance, we'll be able to compute the muscle force straight away. All right, so if we sum the moments around the back joint, remember Jx and Jy in this case are not going to appear into the equation. Okay. All right, and so let's go ahead and sum those moments. We have minus Fm multiplied by A. Okay. And so if you look at Fm and the type of moment that it's going to produce around the back joint, it's a clockwise moment, so we're going to put a negative sign there. Plus the moment that's associated from the normal force, and so we have W top, L, and its moment arm is C. So W top WL is going to produce a counterclockwise moment around the back, and so we give it a positive sign. And then we have the moment associated with the leg. That is a clockwise moment. Yes. And so the clockwise moment will be give it a negative sign. All right. Let's go ahead and solve this equation for Fm. If Fm is equal to, we have W top plus WL multiplied by C minus W leg multiplied by B, all divided by A. So let's go ahead and plug in our numbers here. You're going to see that most of the terms are going to cancel out. And so if you have W top plus WL, remember WL is 0.3 times W top, and so in total we have 1.3 W top multiplied by C, and so C in this case is 0.12 H. And then we have the weight of the leg. Weight of the leg is actually helping to kind of stabilize this a little bit. So we have 0.4 W top multiplied by B, where B is 0.08 H. And then our measurement A here is 0.02. All right, so we're going to see that all the H's are going to cancel out. And when you work through the algebra for this, what we get is Fm is equal to 6.2 W top. All right, so to put this in perspective, you know, if W top, you know, for a typical person, probably is around maybe 100 pounds, maybe more. Okay. What this means is that your spinal erector muscles are actually going to be exerting, you know, almost 650 pounds. And so in this case, 620 pounds. All right, so that's really significant because, you know, unlike the other parts of the body where you have kind of multiple muscles and from multiple different angles that's kind of helping you to, you know, lift the load, the spinal erector muscles, it's a group of muscles. And so it's not just one muscle, but, you know, we kind of usually group them all together because they produce the same motion, right? The spinal erector muscles are kind of by themselves. So they don't really get a lot of help from your oblique muscles. And they definitely don't get any help from your abdominals because they kind of use the opposite motion. So this is all from the same kind of muscle. But I think more importantly is kind of the stress that it puts on your joints. Okay. So let's take the muscle force and let's compute the joint reaction forces that are those. And just remember that, you know, when we compute the joint reaction forces, you know, most time it's going to be a compressive force, right? And so it's going to be force, you know, a joint reaction force is just a measure of just how much compressive force you're applying at that. Okay. And so all of this kind of compressive force that we're going to be computing is going to be placed on your vertebrae bones, and more importantly, kind of placed on your intervertebral discs. Okay. So let's go ahead and sum this up. We have some of the forces in the x direction, and so in the x direction we only have two forces here. So we have jx minus plus, excuse me, Fm sine theta. We have sine theta here because we define theta with respect to the vertical line. Okay. And so we solve for this, we get jx is equal to minus 4.38 W top. Okay. All right, so let's do the same thing in the y direction. So let's sum the forces in that direction. So we have jy plus Fm cosine theta minus W leg plus W top L equal to 0. Okay. We have a fairly straightforward calculation here. So, you know, just go ahead and plug in and we solve for jy. We get jy is equal to minus 5.28 W top. And so of course we get negative numbers here, and so all that negative basically means is that the actual direction of the joint reaction force is just opposite of what we drew, okay? So that's what we find. Okay. And then finally, just to kind of get a sense of the overall magnitude of the joint reaction force, let's take the magnitude of these two. All right, so to take the magnitude, Jx and Jy, they're both components of the same vector. So you take the square root of Jx squared plus Jy squared. When we compute that magnitude, this is 6.86 times W. Again, this is pretty massive. So you're talking about a typical person with W top of about 100 pounds. Then this is almost 700 pounds of force that's being applied at your back. Okay. All right. Any questions on this? Okay. All right. And so this is a lot of force, but it's also it's a lot of force, but also not that much higher than what we've seen, right? Especially when we're talking about the lower extremity. And so 700 pounds of force, yeah, it seems like a lot, but your legs, your quadricep muscles, your thigh bones, things like that, all of those are kind of, you have forces in these kind of ballparks pretty regularly, especially when you kind of exert yourself physically, when you're running or sprinting or jumping or things like that. So, this is a large amount of force, but nothing too extreme. But this amount of force is actually kind of really significant for your back because of the anatomy and because of the geometry of your vertebrae bones. Okay. Because unlike the lower extremity where we don't have that many bones, right? So you have just one femur and you have two kind of lower leg bones, right? And so there's not as many moving parts in the lower extremity. Okay. But in your spine, you have all these kind of little vertebrate bones, which are little relative to the other bones in your body, and they're all kind of interconnected. And so you have a lot more of this kind of these discs and soft tissues. Okay. So there are a lot more bones, a lot more joints, a lot more soft tissue in between them. Okay. And so when you place loads on your vertebrae, it's a lot more sensitive to these things than other parts of your body. Okay. And so let's draw an analogy with kind of a mechanical example, right? And so if we have kind of if we're building a structure, right? And so let's say that we're building a structure, just like we'll kind of draw a direct comparison. So let's draw a pole, right? And so a supporting column for a building. So usually when you're drawing a supporting column, for a building, you can kind of actually see one right outside the class, right? It's usually one solid material, right? We don't draw any joints, we don't draw any kind of breaks in this column. Now imagine you drew that, you made that exact same column, but instead of kind of having one solid material, instead you're having it made of like lots of little materials with with kind of glue in between. Have some glue in between. You get the idea, so you can kind of continue. Just by the fact that there's so many more parts here, it's not going to be as structurally sound as kind of one big solid material. Okay. And in particular, what we usually say is that the more parts and the more joints that you kind of add more locations or more ways that your structure can fail. And so your spine is kind of the same way. So kind of the more, just because there's so many different vertebrate bones, right? You don't have, it's not like your arm where you essentially just have two bones in your arm. So you have your upper arm and your lower arm, right? You have 33 vertebrate bones, right? And so they all are kind of interconnected and they all kind of have a disc in between. And so when you place stress on your vertebrae and you place stress on your spine, that really kind of squeezes those spaces in between the bones, right? And that can lead to a lot of issues like a hernia or other issues with your, maybe a fracture in your spine or something like that. Okay. And so, your back is very, very sensitive to these kinds of forces. And so, you want to make sure that you're not exposing your back to kind of an undue amount of force, just because, the discs and the vertebrate bones on the inside are just a lot more sensitive to these things than other parts of your body. All right. Any questions on this? Okay. All right. So let's do another example, but now let's see what happens when we lift with proper technique. So visually, it's going to look like this. And so, instead of having straight legs, this person's going to be crouching down. Okay. Let's say that it's like this. It looks better in my notes, trust me. Okay. So just like before, we're going to have our back joint. So let me move it right there. Okay. So we're going to have the same forces here. So we're going to have our muscle force. And so our muscle force is going to be acting just like this. Okay. And we're going to assume that we know the moment arm for the muscle force. And so we're going to give that distance A right there. Okay. We have the weight of the leg. Color. And we're going to assume we know the moment arm here. We're going to give that the symbol B, just like last time. And then finally, we have the weight from the load itself. And so again, we're going to assume that it acts at the toes. And that force has a magnitude of W top plus WL. And we're gonna assume it has a moment arm C. And we have the angle here, theta, just like before. Okay, and so because we're crouching down here, it is going to change our geometry a little bit. Okay, the main thing is that, you know, because your back is more straight, what that does is that it actually increases the value for A, and it reduces the angle theta here as well. And what you're going to see, that's going to be kind of the key here that kind of you know, reduces the load on the spine. Okay. So let's go ahead and put numbers on this. And so we'll say A here is 0.03 H. B here is going to be 0.1 H. C is going to be 0.12 H. Okay. So you can see B is a little bit increased as well, because your legs are a little bit more forward. All right, and so our weights are going to be the same. So our weight of the leg is going to be 0.4 W top. W top is still going to be W top. And then WL is going to be W top as well, or 0.3 W top. Okay. So the loads are the same. And so, you know, we're lifting the same load. The only thing different here is our technique, which is essentially just changing the geometry of the problem. Okay. Oh, theta. And so we'll assume theta is 20 degrees. Okay. So let's run through the calculations again. And so you know, we'll go fairly quickly this time because the equations are essentially going to be the same. Okay. And then we'll see, what you'll see is that both the muscle force and the joint reaction forces are going to be significantly lower in this case. Okay. All right, so let's start with the back joints. So let's start with the sum of the moments to compute FM. All right, so if we sum the moments, we get minus FM times A plus W top plus WL times B minus W leg times B. Okay. All of that's equal to 0. So if we solve for FM here is going to have the same result as before. So we're going to say that FM is equal to W top plus WL times B minus W leg B. Oh, sorry. The W top and WL are multiplied by 6. We're almost the same in this case. I'll make sure we fully put it. Okay, and then we're going to divide everything by A. All right, and so if we plug in the numbers for this one, you're going to see H is going to cancel out of every expression here. And so what we get for FM is 3.87 times W top. So still, you know, pretty significant. You know, it's definitely, you know, not, it doesn't trivialize the amount of muscle force, but it's still much less than it was before. So it's about half of what it was before. All right, so let's do the same thing for the joint reaction forces. And so let's go ahead and sum the forces in the x direction. Okay. So we have Jx plus Fm theta is equal to 0. Okay. And so if we solve this equation for Jx, what we get is Jx is equal to minus 1.32 W top. We sum the forces in the y direction, so we have same expressions before. So we have Jy plus Fm cosine theta minus W leg Left W top. Plus WL. Equal to 0. Okay. We solve this expression for JY, we get minus 4.54 W top. And then just like before, let's take the magnitude. So let's take square root of JX squared plus JY squared. With that, we plug in, we get 4.73 W plus. Which again, we get a result that's kind of much lower than what we had when we were lifting with core technique. So that's good. And so, you can kind of see from this example here that, when you lift technique, it still puts a lot of stress on your back. And so, just for general health, you want to limit the amount of lifting that you do on any given day. Okay. But it's still, a lot less than what we had before. So this is good. Okay. All right. Any questions on this? All right. And so let's talk about the differences. So, our equations here are mostly the same, right? And so when we're lifting with good technique and poor technique, it's not really that our equation changes, it's mostly our geometry that changes, right? In particular, the main aspect of the geometry that changes is that of the muscles. And so there are two main things that change. One of which has a bigger impact than the other. Okay. And for the main effect that we have to is the moment arm increase. So that is the value of A. Okay. And so went, I think, from 0.02 H to 0.03 H. Okay. The other main difference here is that the angle gets smaller as well. Okay. And remember that the angle, the way that we define the angle here is a little bit different than what we normally do. We define the angle with respect to the vertical line as opposed to orientation. Okay. And so those are the two main things that kind of improved our result. And so what that tells us is that the main thing that kind of gets you to lift with better technique is not necessarily that you're using your legs, right? So what a lot of people think is that when you lift with your legs, because you're using your leg muscles to kind of help with the load, that takes some load off the back, and that's true to an extent. But the main reason why that that lifting with your legs is better is that it just naturally gets your back into a straighter position. So that's kind of the most important part. So you don't want to kind of arch your back too much when you're lifting. That's usually what's going to lead to injuries. Okay. And if you've ever done any kind of weightlifting, and so if you've ever done deadlifts or anything like that, or any kind of squats or anything like that, that's kind of the main thing that they tell you as well, is that to try to avoid injury when you're doing those lifts, you want to keep your back as straight as possible, and because that's what's going to kind of reduce the amount of load, that your vertebrae have to experience. Okay. Okay. And so a lot of times it's actually kind of good to kind of artificially kind of create this effect. Okay? And so when we talked about kind of the different types of curvature in your back, right? There's one position where it kind of almost like you're kind of sticking your booty out, right? And so that's the lordosis position. And so that's also something good to think about, when you're lifting things off the ground, is, to kind of help you kind of have that good posture, try to imagine you're kind of sticking your butt out, and you're sticking your butt out and you're kind of sticking your stomach forward to kind of make sure that your back is in kind of the best position possible to lift. And as I try to demonstrate right now, I felt my back crack really bad. So I need to follow my own advice sometimes. Another benefit, the kind of lifting with your legs, that kind of naturally, when you try to bend down, it naturally kind of brings the load kind of closer to your body, and so that also kind of reduces the amount of stress that your back does. So when you're lifting with your back, just because your torso is kind of tall, right? What you kind of end up doing is that, the load is kind of over here, right? Right, and so you have kind of this longer distance here that you have to kind of lift from. Okay? And the larger that moment arm is, the more stress that's going to put on your back. Okay? Whereas if you lift with your legs, right? The load is naturally kind of much closer to your body. And so if you kind of measure this distance right here, that's also going to, that's going to be a lot less, and it's going to put less stress on your back. And then one other benefit to lifting with your legs is that, even though it is kind of putting pressure on your vertebrae still, by keeping your back straight, it kind of evenly distributes that load throughout your entire vertebrae. Because when you lift with your back, it almost kind of creates a pinching kind of a motion where it kind of pinches the vertebrae, where most of the stress is placed on either the front or the back, mostly the front. Okay. So we draw the vertebrae here, a very simple picture of it. Okay. And so when you lift with your back, most of the load, okay, is going to be on kind of one end of the vertebrae. And then it kind of tapers off kind of towards the end. Okay. This is bad technique. Because if you kind of are like this, what kind of ends up happening is that your two vertebrate bones kind of become pinched like this. Okay. And so you kind of put a little bit too much force on one side, and what that's going to do is that for the for the disc that's kind of in the middle, normally the disc should kind of just be in the middle, just like this, right? But if you're kind of pinching it to one side, then it kind of almost causes it to kind of like spill out on one side, just like that. Okay. And this right here, when you have your disc bulging like this, this is basically what causes a hernia. And so when you lift with poor technique, that's a lot more likely to happen because most of the load kind of gets pushed on one side of the vertebrae. Okay. Whereas if you lift with good technique, the load kind of gets evenly distributed across the entire vertebrate. Okay. This right here is good technique. So visually what that looks like is that when you have, the load kind of evenly distributed, you don't kind of have this pinching effect anymore. So, you kind of compress the entire vertebrate together all under the same load. So, and so your disc in there is going to compress, but it's much less likely to kind of spill out because there's no kind of pinching that occurs, which is what it's designed for. So it's designed to kind of compress, but you don't want it to be kind of spilled. All right, so another benefit to kind of lifting with your kind of evenly reduce the amount of stress from your back, and then also kind of evenly distribute the load on your. Okay. All right, any questions on this? All right, so let's call it here today. And so on Wednesday when we meet up again, we'll be taking our midterm exam. So again, I'm going to send an announcement later today to kind of clarify all the points, clarify what you've been doing and kind of what you can expect from the exam. Remember to look at the study guide for the conceptual problems, look at the homeworks or any of the additional practice problems for the analysis, and if you can do all those things, you're going to be in great shape for these. If you have, of course, any last minute questions, I have office hours tomorrow. And if those times don't work for you, just let me know, and then we can find time to meet outside. All right, thank you guys for coming today. Good luck with your study, and I will see you all here on Wednesday. So for the good posture one, for the good posture, your back is not going to be doing it. It's going to be all your. So for part A, FMA is going to be the one that's FMB you can just seriously right. Like for the second part of the core posture, it's the opposite.
Yes, you can use it. Because I consider use both of this and.
Oh, yeah, you can't solve this too many unknowns. Yes, yeah, so if you're coming to office hours, you don't have
Just
to.
the virtual in North.
Yeah, so if you come to office hours, you can just show us, but if you wanna meet outside of office hours, let me know. You can- Like, always be time. Tomorrow.
Oh, yeah.
And so, but that's pretty fun, that can be.
No, I'm not. I mean, I would say. Yeah, I have two, three.
Anything, you have a question on?
That's pretty good.